Proxima Centauri is the closest star to our Sun. It sits just 4.24 light-years away. Astronomers call it our nearest neighbour. That word, nearest, hides a lie so enormous it should terrify every person alive. If you launch the fastest object humanity has ever built directly at Proxima Centauri today, it would not arrive for nearly 7,000 years. Every civilization that currently exists on Earth would be dust long before the spacecraft crossed even a fraction of that distance. But the travel time is not the worst part. The worst part is what happens if you try to go faster. Speed does not solve the problem. Speed creates new ones. Radiation, impact, energy, isolation, decay. Every solution to the distance becomes its own way of dying. If you want to understand why the nearest star might as well be on the other side of the universe, consider hitting that like button and subscribing. It helps more than you know, and I appreciate every single one of you who supports the channel. Now, settle in and get yourself comfortable. Let's begin. There is a phrase in astronomy that sounds like a gift. The nearest star. Say it aloud and it feels almost welcoming, as if the universe placed a stepping stone just outside our door, a convenient waypoint waiting for us to reach it, whenever we finally build a ship fast enough. Textbooks use this phrase casually. Documentaries drop it like a promise. The nearest star, Proxima Centauri, sitting right next door in cosmic terms, only 4.24 light-years from our Sun. The implication is always the same. If we can just solve the engineering, the nearest star is within reach. That implication is a lie, not a small lie, not a rounding error or an optimistic simplification. It is a lie so vast that the human brain physically cannot hold the truth it conceals. 4.24 light-years is not a distance you can intuit by scaling up anything you have ever experienced. It is not like saying the moon is far away, or Mars is very far away, or even that Pluto is unimaginably far away. Those distances are real. Those distances have been crossed by spacecraft built with human hands. 4.24 light-years sits in a completely different category. It is the distance where human engineering, human biology, and human patience all begin to collapse simultaneously. And the terrifying part is that Proxima Centauri is the closest star there is. If this distance defeats us, every other star in the galaxy is worse. But before you can feel the true weight of that distance, you need to understand what Proxima Centauri actually is. Proxima Centauri is a red dwarf. It is a small, cool, dim star with a surface temperature of roughly 3,100 Kelvin, about half the temperature of our Sun. It carries roughly 12.5% of the Sun's mass and about 14% of its diameter, making it roughly 1.5 times the size of the planet Jupiter. Despite being the closest star to our solar system, it is completely invisible to the naked eye. You cannot walk outside tonight and find it in the sky. It is simply too faint. Its total energy output across all wavelengths is approximately 0.17% of the Sun's, and its visible light output is even lower because most of its radiation emerges in the infrared, wavelengths the human eye cannot detect. The star was discovered in 1915 by the Scottish astronomer Robert Innes, working at the Union Observatory in Johannesburg, South Africa. Innes noticed that a small, faint star, a few degrees from the bright Alpha Centauri binary system, had an unusually large proper motion across the sky. When the distance was measured, it turned out to be closer to our Sun than any other known star. Innes named it Proxima, from the Latin word meaning nearest. Proxima Centauri is the third member of the Alpha Centauri system. Alpha Centauri A and Alpha Centauri B form a binary pair, two Sun-like stars orbiting each other relatively closely. Proxima orbits this central pair at an enormous distance of roughly 13,000 astronomical units, so far out that it takes approximately 550,000 years to complete a single orbit. Some astronomers have questioned whether Proxima is truly gravitationally bound to the inner pair at all, or whether it might simply be passing through the same region of space on a temporary trajectory. Current evidence suggests it is bound, but the connection is tenuous. Proxima lives on the fringes of its own star system, a loner among loners. What makes Proxima Centauri more than a dim curiosity is its planets. In 2016, The European Southern Observatory announced the discovery of Proxima b, a planet with a minimum mass of roughly 1.1 Earth masses orbiting within the star's habitable zone. That discovery electrified the world. Here was an Earth-sized planet, orbiting the closest star to our Sun, sitting at a distance where liquid water could theoretically exist on its surface. In 2022, a second candidate was announced, Proxima d, a sub-Earth with barely 1/4 the mass of our planet, orbiting extremely close to the star with a period of just 5.1 days. Proxima d was independently confirmed in 2025 using the Near-Infrared Planet Searcher instrument. A third candidate, Proxima c, a possible super-Earth or mini-Neptune orbiting much farther out, remains under investigation. 3 known planets around the nearest star. The temptation to call this a destination is almost irresistible, but the word destination implies that you know what you are travelling to, and the unsettling truth about Proxima b is how little we actually know. The planet's mass is not confirmed. What we have is a minimum mass, roughly 1.1 times that of the Earth, derived from the radial velocity method, which measures the wobble that a planet induces in its host star. The true mass depends on the orbital inclination, the angle at which the planet's orbit is tilted relative to our line of sight. If the orbit is nearly edge-on, the true mass is close to the minimum. If the orbit is significantly inclined, the planet could be substantially heavier, perhaps 2 or 3 Earth masses, which would change its likely composition, its atmosphere, and its surface conditions entirely. We do not know the inclination. We do not know the radius with useful precision because Proxima b has not been observed to transit across the face of its star. Without a radius, we cannot calculate the planet's density, which means we cannot determine whether it is a rocky world like Earth or something with a thick, volatile envelope, more like a miniature Neptune. Proxima b is almost certainly tidally locked. This means one hemisphere permanently faces the star, baking under continuous radiation, while the opposite hemisphere faces away into permanent darkness and cold. If the planet has a substantial atmosphere, heat might circulate between the two sides, creating a potentially temperate zone along the terminator, the ring of permanent twilight between the day and night hemispheres. If the planet has no atmosphere, the contrast is extreme. The day side could approach the boiling point of water, baking under the star's unbroken glare. The night side would plunge hundreds of degrees below freezing. The surface would be split between a scorched desert and an ice sheet, with no moderate zone between them. We do not know whether Proxima b has a magnetic field. Without one, the stellar wind and flare radiation from Proxima Centauri would continuously bombard the planet's surface, scouring away any atmosphere and sterilizing the ground. We do not know whether the planet has surface water, or ever had surface water, or possesses any of the chemical precursors for biology. We are projecting an entire world's characteristics from a measurement of a wobble in starlight. Proxima b is less a known destination and more a set of optimistic assumptions projected onto a dot of reflected infrared. It is the nearest potentially interesting exoplanet, not the nearest confirmed habitable world. The distinction is critical, and it will become devastating later in this story. But calling it a destination requires crossing the distance, and the distance is where everything falls apart. 4.24 light-years. Say it quickly and it sounds manageable. 4 is a small number. Light-years sound like a tidy unit, but a light-year is not a human measurement. A light-year is the distance that light, moving at 186,282 miles per second, covers in one full year of continuous travel. That works out to approximately 5.88 trillion miles. 1 light-year, nearly 6 trillion miles. Now multiply that by 4.24. The distance to Proxima Centauri is approximately 25 trillion miles. Written with all its zeros, that number stretches across the page like a sentence that refuses to end. 25 followed by 12 zeros. To make this distance even slightly tangible, consider that the Sun sits roughly 93 million miles from Earth, 1 astronomical unit. Proxima Centauri is approximately 268,000 astronomical units away. That means the gap between our Sun and the nearest star is roughly 268,000 times the distance between the Earth and the Sun. That number still feels abstract, so try it this way. Imagine the entire solar system, from the Sun out to the orbit of Neptune, compressed down so that it fits on a single penny. At that scale, Proxima Centauri would be another penny sitting on a football field. Not at the far end of the football field, not across the stadium, on a football field that is over 400 feet away from you. The entire solar system, every planet, every moon, every asteroid, the sun itself reduced to the size of a coin. And the nearest star is still a football field away. That is the gap. That is what 4.24 light-years means in terms you can almost visualize but still cannot truly feel. The emptiness between those two pennies is the interstellar void, and nothing humanity has ever built has come close to crossing it. And that emptiness is not merely a number. It is a physical space, and it is the most featureless environment in the known universe. Between our solar system and Proxima Centauri, there are no stars, no planets, no asteroids. After the first light year or so, no comets, no landmarks of any kind. A spacecraft departing Earth would watch the sun shrink behind it, dwindling from the brilliant disk that dominates our sky to just another star, then to a faint point indistinguishable from the background. Ahead, Proxima Centauri would remain invisible to the naked eye for most of the journey, too dim to resolve against the blackness. Between those 2 points, the view out of every window on the ship would be identical. Stars scattered across the sky in patterns that change so slowly that years of travel produce no perceptible shift. No coastlines, no mountain ranges, no planetary crescents growing larger in the viewport. Nothing to confirm progress except onboard instruments measuring a distance that shrinks in increments too small to feel. Every journey humanity has ever undertaken has offered intermediate landmarks. Sailors followed coastlines, pilots watched terrain pass below. Even Apollo astronauts watched the moon grow in their windows over 3 days. The interstellar crossing offers none of this. The crew would spend the entirety of the voyage suspended in a void so featureless that the only external evidence of motion is the imperceptibly slow dimming of the sun behind them, and the equally imperceptible brightening of a star ahead that they cannot even see without instruments. This emptiness is not merely spatial, it is sensory, it is psychological. It is a journey through nothing, toward a destination that remains invisible for most of the trip, with no confirmation that the ship is even moving except the readout on a navigation screen. No human being has ever experienced isolation this complete, and this is the environment that every interstellar traveler would inhabit for years, decades, centuries or longer. This is where the travel times begin to destroy any remaining comfort. Voyager 1 is the most distant human-made object in existence. Launched in 1977, it has been travelling away from Earth for nearly 5 decades. It crossed into interstellar space in 2012, passing beyond the boundary of the Sun's heliosphere, and as of mid-2026, it sits over 165 astronomical units from the Sun. That is an extraordinary achievement. It is also laughably insufficient. 165 astronomical units sounds impressive until you remember that Proxima Centauri is 268,000 astronomical units away. Voyager 1 has crossed roughly 0.06% of the distance to the nearest star, after almost 50 years of flight. Voyager 1 travels at approximately 38,000 miles per hour relative to the Sun. At that speed, it covers about 3.6 astronomical units per year. If it were aimed at Proxima Centauri, which it is not, it would arrive in approximately 73,000 years. 73,000 years. To place that in human terms, 73,000 years ago, modern humans shared the planet with Neanderthals. The last ice age had not yet reached its peak. Agriculture did not exist. Written language did not exist. Civilization as we understand it was tens of thousands of years in the future. The entire recorded history of the human species, every empire, every war, every invention, every piece of music ever composed, fits inside the last 5,000 years. Voyager 1 would need more than 14 times that span to reach the nearest star. But Voyager 1 is not the fastest object humanity has built. The Parker Solar Probe holds that record. By diving close to the Sun and using its immense gravitational pull to accelerate, the Parker Solar Probe reached a peak speed of approximately 430,000 miles per hour during its closest solar approach in December 2024. That is roughly 192 kilometers per second. It is fast enough to cross the distance from New York to Los Angeles in less than 30 seconds. It is the most extreme velocity any human-made object has ever achieved. Even at that speed, the Parker Solar Probe would need approximately 6,800 years to reach Proxima Centauri. 6,800 years ago, the Egyptian pyramids had not been built. Stonehenge did not exist. The Bronze Age was just beginning, the fastest thing humanity has ever created, travelling without interruption for a span longer than the entirety of recorded civilization, still would not be enough to reach the closest star. New Horizons, the spacecraft that famously flew past Pluto in 2015, launched at the highest Earth escape velocity ever achieved, roughly 36,000 miles per hour. At that speed, the journey to Proxima Centauri would take approximately 78,000 years. Pioneer 10, the first spacecraft to fly past Jupiter, departed the solar system at roughly 32,000 miles per hour. Its travel time to Proxima Centauri would exceed 80,000 years. Now, consider the most fundamental propulsion technology humans possess: chemical rockets, the engines that carried Apollo astronauts to the moon, and that still launch every satellite and space station module into orbit. Chemical rockets produce thrust by burning fuel, typically liquid hydrogen and liquid oxygen, and expelling the exhaust at high speed. The exhaust velocity of the best chemical rockets maxes out at roughly 4.5 kilometers per second. Applying the Tsiolkovsky rocket equation, which governs all reaction-based propulsion, a chemical rocket can accelerate to a final velocity of approximately 13,200 meters per second, or about 29,700 miles per hour. That is 0.0044% of the speed of light. At that velocity, reaching Proxima Centauri would take approximately 98,000 years. 98,000 years on a chemical rocket. Let that register. Chemical propulsion, the only technology that has ever carried human beings off the surface of this planet, is not merely insufficient for interstellar travel, it is irrelevant. The travel time exceeds the entire span of anatomically modern human existence. You could launch a chemical rocket toward Proxima Centauri on the day Homo sapiens first appeared on Earth, and it still would not have arrived. This is the moment when the word nearest begins to crack. Proxima Centauri is the closest star. It is the absolute best case, the most favourable starting point, the shortest possible interstellar journey. And the shortest possible interstellar journey, using the best propulsion technology humanity has ever used to carry people, takes nearly 100,000 years. There is no incremental improvement that fixes this. You cannot make a chemical rocket 10% faster and suddenly the problem becomes manageable. The gap is not a crack in the sidewalk that better shoes can step over. The gap is an ocean. And the difference between interplanetary and interstellar travel is not a difference of degree. It is a difference of kind. Every distance humanity has ever crossed in space exists within the sun's gravitational neighborhood. The moon is 1.3 light seconds away. Mars, at its closest, is about 3 light minutes away. Jupiter, roughly 33 light minutes. Neptune, the outermost major planet, is approximately 4 light hours from the sun. Even Voyager 1, the most distant human-made object, is barely 23 light hours from Earth. These are all distances measured in light seconds, light minutes, and light hours. They are small enough that spacecraft can reach them within human lifetimes using existing technology. Proxima Centauri is measured in light years. That single shift in unit, from hours to years, represents a chasm so wide that every propulsion system humans have ever built falls into it and vanishes. Consider this comparison. The distance from the Earth to the Moon is roughly 1.3 light seconds. A human being has crossed that distance. It took 3 days. The distance to Proxima Centauri is approximately 134 million light seconds. If you think of the Earth-Moon trip as a single step, reaching Proxima Centauri is equivalent to walking the circumference of the entire Earth. 1 step versus a journey around the planet. That is the ratio. That is what nearest means. And yet the distance alone, staggering as it is, does not capture the full horror. Distance is a passive obstacle. It simply exists. You can stare at it and feel despair, but it does not actively try to kill you. The true nightmare begins when you try to solve the distance, because the only way to make the travel time shorter is to go faster. And the moment you go faster, you enter a regime of physics where the interstellar medium stops being empty space and starts being a weapon. At the speeds required to cross 4.24 light-years in anything resembling a human lifetime, individual atoms of hydrogen become high-energy projectiles. Dust grains weighing less than a grain of sand carry the kinetic energy of explosives. Cosmic radiation that Earth's magnetic field deflects without effort becomes an unshielded storm of particles that shred DNA and erode materials with every passing year. Speed, the only apparent solution to the distance problem, generates its own cascade of lethal consequences. The interstellar medium is not empty, it is dilute, and at relativistic velocities, dilute is more than enough to destroy anything that passes through it. This is the trap that Proxima Centauri sets for human ambition. Go slowly and time destroys you. Go quickly and physics destroys you. The distance demands speed. The speed demands shielding, energy, and materials that do not yet exist. And even if you solve every engineering challenge, the destination itself waits at the end of the journey with its own set of threats that have nothing to do with how you got there. But the engineering challenges deserve a closer look, because humanity has not been idle. For decades, physicists and engineers have proposed propulsion concepts that could, in theory, push spacecraft to a meaningful fraction of the speed of light. Nuclear pulse drives, fusion engines, laser-propelled sails. Each concept offers a tantalizing reduction in travel time. Each concept also carries a cost so severe that the cure begins to look as dangerous as the disease. The journey to Proxima Centauri does not get easier when you go faster. It gets different. The category of danger shifts. The flavor of the crisis changes. But the crisis never disappears. It simply transforms from one type of impossible into another. And every transformation reveals a new layer of the problem that the word nearest was quietly concealing all along. What follows is the story of what happens when you try to close the gap. Not with hope, not with speculation, but with the actual physics of acceleration, impact, radiation, and energy. The universe has rules, and the rules do not care that Proxima Centauri is close. The distance demands speed. That much is obvious. When 98,000 years is your baseline, the only rational response is to find a way to go faster. Dramatically faster. Not twice as fast or 10 times as fast, but hundreds or thousands of times faster than anything humanity has ever launched toward the outer solar system. The physics is simple. If you want to cross 4.24 light-years in something resembling a human lifetime, you need to move at a significant percentage of the speed of light. 1% gets you there in roughly 424 years. 5% cuts it to about 85 years. 10% brings the trip down to roughly 42 years. 20%, approximately 21 years. The math is seductive. It whispers that the problem is solvable. Just accelerate harder. And push the engines further. Build something fast enough and the nearest star comes within reach. The math does not tell you what happens to the spacecraft on the way there. The math does not describe what the interstellar medium does to a vehicle moving at 1/10 or 1/5 of the speed of light. And the math does not explain the monstrous energy cost of pushing anything with meaningful mass to those velocities. Speed is not a solution to the distance problem. Speed is a trade. You exchange one category of impossibility for another. The travel time shrinks. The lethality of the journey explodes. But before the exotic concepts, it is worth considering the technologies that represent the next incremental steps beyond chemical rockets. Because if chemical propulsion is irrelevant to interstellar travel, the obvious question is whether better engines that already exist or are under active development can close the gap. The answer is swift and discouraging. Ion propulsion has been used on real spacecraft. Deep Space One, launched in 1998, and the Dawn mission, which explored the asteroid belt, both used ion thrusters that electrically accelerate charged particles and expel them at exhaust velocities roughly 10 times higher than the best chemical rockets. Ion drives are more efficient by a wide margin. They extract far more velocity from each kilogram of propellant. They are also spectacularly weak. The thrust produced by an ion engine is measured in fractions of a newton, less force than the weight of a single sheet of paper resting on your palm. Ion drives do not roar to life and slam astronauts into their seats, they whisper. They push with a force so gentle it is barely measurable, sustained over months and years, gradually building speed through patient accumulation. At the velocities ion-driven spacecraft have achieved, roughly 25,000 miles per hour. In the case of Dawn, the crossing to Proxima Centauri would take over 100,000 years, longer than a chemical rocket. The higher efficiency is offset by the lower thrust and the practical limits on how much propellant can be carried. Ion drives are better than chemical rockets, in the same way that walking is better than crawling when you need to cross an ocean. The improvement is real. The improvement is irrelevant. Nuclear thermal propulsion is more promising in principle. A nuclear thermal rocket uses a fission reactor to heat propellant, typically hydrogen, to extreme temperatures and expel it at roughly twice the exhaust velocity of chemical engines. NASA's NERVA program ground-tested functional nuclear thermal engines in the 1960s, demonstrating that the technology works. Nuclear thermal propulsion is currently under active development for future Mars missions, where it could cut transit times from 7 months to roughly 3 or 4 months. It is the most advanced near-term propulsion upgrade in any space agency's portfolio, but doubling the exhaust velocity does not halve the interstellar travel time. The rocket equation is logarithmic, not linear. Doubling exhaust velocity improves the mass ratio significantly for planetary missions, where the required velocity change is modest. For interstellar velocities, the improvement is marginal. A nuclear thermal rocket can reach perhaps 50,000 to 60,000 miles per hour with practical fuel loads. At that speed, Proxima Centauri is still roughly 45,000 years away. The technology that will eventually carry astronauts to Mars cannot make a meaningful contribution to interstellar travel. The gap between planets and stars is not a gap that incremental propulsion improvements can bridge. It is a gap that requires a fundamentally different approach to generating speed. And so the concepts become radical, because humans have not simply sat idle dreaming about interstellar travel. For more than 70 years, physicists and engineers have designed, calculated, debated, and in some cases partially tested propulsion systems intended to push spacecraft to interstellar velocities. Every single one of these systems reveals, in its own way, how savage the requirements truly are. The earliest serious proposal was Project Orion. Conceived in the late 1950s at General Atomics in San Diego, Project Orion proposed propelling a spacecraft by detonating nuclear bombs behind it. The concept is exactly as brutal as it sounds. A series of small nuclear explosions would be directed against a massive steel pusher plate mounted on the rear of the ship. Shock absorbers would translate each detonation's impulse into forward thrust. The physicist Freeman Dyson served as chief scientist on the project until its cancellation in 1963, driven largely by the Partial Nuclear Test Ban Treaty, which prohibited nuclear explosions in space. Despite its cancellation, Project Orion remains one of the few interstellar propulsion concepts that could theoretically be built using technology that already exists. Nuclear weapons work. Pusher plates can be engineered. The physics is proven. Dyson calculated in his 1968 paper, titled Interstellar Transport, that an Orion-type vehicle could reach roughly 3.3% of the speed of light using an optimistic configuration. At that velocity, the journey to Proxima Centauri would take approximately 128 years. A more aggressive design, with a smaller pusher plate positioned closer to each detonation, could theoretically approach 5% of light speed, cutting the crossing to roughly 85 years. 85 years is not a human lifetime, but it is close. It is conceivable that a crew born aboard the ship could live to see arrival. The engineering cost, however, is staggering. The fuel is nuclear bombs, thousands of them. Each detonation irradiates the spacecraft and everything behind it. The pusher plate must survive repeated nuclear blasts without cracking, warping, or ablating away. The shock absorbers must function flawlessly across decades of continuous operation. The treaty that killed Project Orion still exists, and the estimated cost would run into the trillions of dollars, a figure so large it currently exceeds the total annual economic output of most nations on Earth. After Orion came the fusion concepts. Project Daedalus, studied between 1973 and 1978 by the British Interplanetary Society, designed an uncrewed interstellar probe powered by nuclear fusion. The concept used pellets of deuterium and helium-3, ignited by electron beams inside a reaction chamber to produce a continuous stream of plasma thrust. The original Daedalus design targeted Barnard's star, roughly 6 light-years away, and proposed reaching approximately 12% of the speed of light with a transit time of about 50 years. Adjusted for Proxima Centauri, the crossing would take roughly 36 years at that velocity. An extraordinary number. A human lifetime, a single generation. But Daedalus was uncrewed. The spacecraft massed over 50,000 tons at launch, most of which was fuel. It was a one-way flyby mission, not designed to slow down or enter orbit. And the fuel, helium-3, barely exists on Earth. The most promising source is the atmosphere of Jupiter, where helium-3 could potentially be mined in vast quantities. Mining the atmosphere of Jupiter to fuel an interstellar probe is not a plan. It is a plan to build the infrastructure to make a plan. The technological ladder between where humanity stands today and the launch of a Daedalus-class vehicle has so many missing rungs that the ladder is more gap than structure. Project Icarus, a 21st century successor study, attempted to update Daedalus using 3 decades of technological progress. Icarus retained the fusion drive concept, but aimed to fully decelerate a 150-ton scientific payload into orbit around Alpha Centauri, addressing one of the critical failings of the original design. The proposed crossing time was roughly 100 years, a century of travel, still within the realm of a multi-generational mission. But a century is not a number that inspires confidence in any system's reliability. Then there is the fuel that physics itself seems to have designed for interstellar travel: antimatter. When a particle of matter meets its antimatter counterpart, both annihilate completely, converting 100% of their combined mass into energy. No other reaction in nature achieves this. Nuclear fission converts roughly 0.1% of its fuel mass into energy. Nuclear fusion converts roughly 0.7%. Antimatter annihilation converts everything. 1 gram of antimatter reacting with 1 gram of normal matter releases approximately 180 trillion joules of energy, more than the energy released by the Hiroshima bomb from a combined fuel mass lighter than a small coin. In theory, an antimatter-powered spacecraft could reach 10 or even 20% of the speed of light, with a fuel-to-payload ratio that is merely difficult rather than absurd. A few kilograms of antimatter, carefully reacted with an equal mass of normal matter and directed through a magnetic nozzle, could accelerate a modest spacecraft to interstellar velocities. The travel time to Proxima Centauri drops to decades. The concept sounds almost reasonable. Then you ask where the antimatter comes from. Humanity produces antimatter in particle accelerators. Facilities like CERN generate antiprotons by smashing protons into metal targets at enormous energies. The yield is spectacularly small. The total amount of antimatter produced by every particle accelerator on Earth in the entire history of the field is estimated at roughly 20 nanograms, 20 billionths of a gram. At current production rates, manufacturing a single gram of antimatter would take approximately 100 million years and cost on the order of $60 trillion. An interstellar mission requiring several kilograms of antimatter would demand production rates billions of times higher than anything that currently exists, sustained for decades, at costs that exceed the total economic output of human civilization. And production is only the first problem. Antimatter cannot touch normal matter. Any contact results in instant annihilation. Storing antimatter requires suspending it in a perfect vacuum inside magnetic or electric fields that prevent it from touching the walls of its container. As of the mid-2020s, the longest antimatter has been held in laboratory conditions is hours for small clusters of antihydrogen atoms and over a year for individual antiprotons, both at CERN. But these experiments involve individual atoms, not usable quantities. Storing kilograms of antimatter for years or decades during a spacecraft's acceleration phase requires containment technology that does not exist and that no proposed design has credibly demonstrated. A single containment failure, one microscopic breach in the magnetic bottle, would produce a catastrophic explosion inside the spacecraft. Antimatter is the most energy-dense fuel physically possible, and it is also the most dangerous material imaginable. The universe offers perfection, and then places it behind a wall of impossibility so high that even acknowledging its existence feels like a cruel joke. After antimatter, the next logical step is to stop carrying fuel entirely. If onboard fuel creates impossible mass ratios, then collect fuel along the way. The interstellar medium contains hydrogen. A spacecraft equipped with a large magnetic scoop could, in theory, funnel incoming hydrogen into an onboard fusion reactor, burn it for thrust, and accelerate indefinitely without ever running out of propellant. This concept, proposed in 1960 by the physicist Robert Bussard, became known as the Bussard ramjet. For decades, it represented the most optimistic vision of interstellar travel, a ship that feeds on the void itself, accelerating forever, limited only by the speed of light. The concept is elegant. The reality is devastating. The interstellar medium near our solar system contains roughly 1 hydrogen atom per cubic centimetre. To collect enough hydrogen to fuel a fusion reactor producing meaningful thrust, the magnetic scoop would need to be enormous, hundreds of kilometres in diameter, generating magnetic fields strong enough to ionize and capture hydrogen atoms scattered across unimaginable volumes of space. Even with such a scoop, the collection rate at low speeds is too small to produce significant thrust. The ship must already be moving fast to sweep through enough volume per second for the reactor to function, but accelerating to that initial speed requires onboard fuel, which reintroduces the mass ratio problem the ramjet was supposed to solve. And then comes the final blow. At relativistic speeds, the very hydrogen the scoop collects creates drag. Each captured atom must be decelerated from the spacecraft's frame velocity to 0 before it can be fed into the reactor. That deceleration transfers momentum from the atom to the scoop, producing a braking force. Calculations performed in the decades after Bussard's original proposal demonstrated that at speeds above a few percent of light speed, the drag from the incoming hydrogen exceeds the thrust produced by fusing it. The ramjet does not accelerate, it slows down. The interstellar medium, far from being a free fuel source, becomes a wall. The faster you go, the harder the wall pushes back. The concept that was supposed to eliminate the fuel problem turns out to make the fuel problem worse. The universe offered a gas station between the stars, and then arranged the physics so that stopping at the gas station costs more energy than driving past it. Then came the concept that made headlines, Breakthrough Starshot, announced in 2016 by billionaire Yuri Milner, with endorsements from Stephen Hawking and Mark Zuckerberg. Starshot proposed something radically different from nuclear drives. Instead of accelerating a massive ship with onboard fuel, Starshot would use an enormous ground-based laser array to push a tiny spacecraft equipped with a reflective sail. The sail would be just a few meters across. The spacecraft behind it, called a starship, would weigh roughly 1 gram. 1 gram. The mass of a paperclip, accelerated by a laser beam delivering roughly 1 terajoule of energy over approximately 10 minutes, the starship would reach 20% of the speed of light. At that velocity, the crossing to Proxima Centauri would take just over 20 years. 20 years to the nearest star. The number is breathtaking. It sits within a single human career. A mission launched today could return data before the scientists who designed it retire. For a brief moment, interstellar travel seemed not just possible but imminent. Then the details surfaced. A 1-gram spacecraft carries no meaningful scientific instruments by current standards. No high-resolution camera, no spectrometer, no magnetometer. The entire probe must be miniaturized beyond anything that exists. The laser array required to accelerate even this tiny sail would need to produce roughly 100 gigawatts of power, comparable to the entire electrical output of a mid-sized country, focused into a beam and sustained for 10 minutes per launch. The sail must survive this bombardment without melting, tearing, or deforming. The spacecraft must survive a journey through 4 light-years of interstellar medium at 20% of the speed of light, a hazard profile that, as we will see shortly, is severe even for a gram-scale object. And at the end of the trip, the starship has no way to slow down. It blasts through the Proxima Centauri system at 60,000 kilometers per second, spending mere hours within observational range of any planet. Everything it sees must be captured and transmitted back to Earth using a laser so small it can barely be detected across 4 light-years of space. By 2025, Breakthrough Starshot was effectively dead. Scientific American reported in September of that year that the program had been placed on indefinite hold. No formal cancellation was announced, but researchers working on its technical problems lacked clarity about its future. The total expenditure across approximately 30 research contracts came to roughly $4.5 million. The concept remains theoretically valid. The engineering remains decades away, and it applies only to gram-scale probes, not to humans, not to anything large enough to carry a crew, supplies, or meaningful life support systems. Starshot was never a plan to send people to Proxima Centauri. It was a plan to send a paperclip. These are the best propulsion concepts humanity has produced in 70 years of serious study. Nuclear bombs, fusion engines, continent-sized lasers, perfect fuel that cannot be manufactured, and free fuel that creates drag instead of thrust. Each one shaves years off the crossing time. Each one demands technology, energy, and resources so far beyond current capability that the gap between concept and reality is itself an abyss. To understand why that gap is so stubborn, it helps to put concrete numbers on the energy cost of interstellar speed, not abstract ratios, actual numbers. Consider a spacecraft with a 100-ton dry mass. That includes the habitat, the crew, the life support systems, the shielding, the structure, and every instrument aboard. 100 tons is modest by any standard. The International Space Station masses over 400 tons, and it supports 6 people for months at a time with constant resupply. 100 tons for a crewed interstellar vessel is optimistic to the point of fantasy, but use it as a starting point. Now apply the Tsiolkovsky rocket equation. To accelerate this 100-ton spacecraft to 5% of the speed of light, using a hypothetical fusion drive with an exhaust velocity of several thousand kilometers per second, within the range of what advanced deuterium fusion concepts propose, the required fuel mass is approximately 6,500 tons. That is a mass ratio of 66 to 1. The spacecraft at launch weighs 6,600 tons, of which 6,500 is fuel and 100 is everything else. The entire ship exists to burn fuel, and the fuel exists to accelerate other fuel. But this calculation covers only acceleration. To stop at the destination, the ship must carry fuel for deceleration as well. Deceleration requires the same change in velocity as acceleration, which means the ship must carry enough fuel to slow the entire vehicle, including the deceleration fuel itself, from 5% of light speed back to 0. Running the equation again with this requirement, the launch mass climbs to over 400,000 tons. 400,000 tons of spacecraft, of which 100 tons is the payload. The mass ratio is 4,000 to 1. For every kilogram of crew, habitat, and equipment, the ship must carry 4,000 kilograms of fuel. At 10% of light speed, the mass ratio becomes grotesque. The launch mass exceeds tens of millions of tons. At 20%, the numbers leave the realm of engineering and enter the realm of planetary-scale resource extraction. The fuel mass required to accelerate and decelerate a 100-ton crewed vessel to 20% of light speed, using the best theoretical fusion drive, is roughly comparable to the mass of a small asteroid. You do not build this spacecraft. You mine a world to fuel it. Laser propulsion avoids the rocket equation entirely by keeping the energy source on the ground. That is its singular genius. The spacecraft carries no fuel. The laser does all the work. But laser propulsion only works during the acceleration phase, while the spacecraft is still close enough to the laser for the beam to remain focused on the sail. Once the ship is too far away, the beam spreads, the push fades, and the spacecraft coasts. It cannot accelerate further, it cannot decelerate, it cannot adjust course, and it carries no onboard propulsion to do any of these things, because the entire point of laser propulsion is to eliminate onboard fuel. This means laser-propelled craft are, by design, uncontrollable after launch. They fly in a straight line at whatever speed they reach during the acceleration phase, and they stay at that speed until something stops them. For a gram-scale Starshot probe, this is acceptable. The probe was designed as a flyby. It screams through the target system, collects what data it can in a few hours, and transmits it home. For a crewed mission, this is suicide. A ship full of human beings cannot perform a flyby at 20% of the speed of light. It must stop, and stopping requires energy that the ship, by design, does not carry. But even if you could build these engines, even if the energy budgets were met and the engineering challenges were solved, the journey would still try to kill you. Because the faster you go, the more hostile the space between stars becomes. The interstellar medium is not empty. This is the fact that transforms speed from salvation into threat. Between the stars, space contains a thin but continuous distribution of gas and dust. The gas is primarily hydrogen, with some helium and trace amounts of heavier elements. The density is extraordinarily low, roughly 1 atom per cubic centimetre, in the local interstellar medium near our solar system. On Earth, a cubic centimetre of air at sea level contains approximately 25 quintillion molecules. By comparison, interstellar space is a vacuum so perfect that no laboratory on Earth can replicate it. But vacuum is relative to speed. A spacecraft moving through this medium at everyday velocities encounters so few particles that the effect is negligible. At a fraction of the speed of light, the equation changes catastrophically. Consider a spacecraft moving at 20% of the speed of light, 60,000 kilometers per second. At this velocity, every hydrogen atom in the flight path becomes a relativistic projectile. In the spacecraft's rest frame, those atoms stream toward it at 60,000 kilometers per second. A hydrogen nucleus moving at that speed carries energy in the mega-electron volt range. It is no longer a harmless atom of gas. It is radiation. A continuous, unbroken stream of radiation produced not by any onboard source, but by the simple act of moving through space. Research published in 2017 by astrophysicist Thiem Hoang and colleagues quantified the damage this bombardment inflicts. At 20% of light speed, incoming hydrogen and helium nuclei penetrate the spacecraft's surface and embed themselves in the material at a characteristic depth determined by their energy. These implanted atoms accumulate over the Fourier crossing, forming gas pockets within the material. The gas pockets grow into bubbles, the bubbles blister, the blisters rupture, the surface delaminates. Layer by layer, the forward-facing surface of the spacecraft is eaten away by the very atoms of interstellar space. For quartz-based materials, the damage reaches a depth of approximately 0.1 millimeters over the crossing to Alpha Centauri. For graphite-based materials, the effect is weaker but still present. This erosion is not theoretical. It mirrors damage observed in fusion reactor components, where plasma-facing walls experience identical gas implantation and blistering processes. The interstellar medium, at relativistic speeds, behaves like a fusion reactor turned inside out, with the spacecraft itself serving as the plasma-facing wall. Dust is worse. The interstellar medium contains solid particles, tiny grains of silicate, carbon and ice, ranging in size from nanometers to fractions of a micrometer. Most are smaller than a wavelength of visible light. At everyday speeds, they are harmless. At 20% of the speed of light, a dust grain weighing a few milligrams carries kinetic energy equivalent to a small explosive charge. The impact does not merely dent the surface. It produces explosive evaporation of the surrounding material. Atoms at the impact site are instantly vaporized, creating a microscopic fireball that melts and deforms the material around the crater. Each impact is a tiny bomb detonating against the skin of the ship. Over 4.24 light-years, a spacecraft sweeps through a column of interstellar medium containing trillions of dust grains. Most are small enough that individual impacts are survivable, but cumulatively, the surface erodes. Research from Lawrence Livermore National Laboratory estimated that dust bombardment at 20% of light speed can erode approximately 0.5 millimeter of surface material over the crossing distance. For a gram-scale probe like Starshot's Starship, 0.5 millimeter is a significant fraction of the entire vehicle. For a larger crewed spacecraft, the shielding requirements escalate dramatically, and the damage is not limited to the surface. At these velocities, even individual atoms of heavier elements like oxygen and iron produce damage tracks inside the spacecraft's material structure. These tracks are nanometers wide and millimeters long, tiny tunnels of disrupted material bored through the solid structure by single incoming atoms. The volume fraction of damaged material accumulates with distance traveled. By the time the spacecraft reaches Proxima Centauri, a measurable percentage of its forward surface has been structurally compromised at the atomic level. The ship arrives damaged by the journey itself, weakened by the very medium it passed through. Now add radiation from another source entirely. Galactic cosmic rays are high-energy particles, primarily protons and heavy atomic nuclei, accelerated to extreme velocities by supernovae and other astrophysical processes throughout the galaxy. They permeate all of interstellar space. On Earth, the atmosphere and the planet's magnetic field deflect or absorb the vast majority of these particles. In deep space, beyond the protection of the Sun's heliosphere, there is no shield. NASA research confirms that the deep space radiation dose from galactic cosmic rays is approximately 0.45 mg per day. Over a 3-year Mars mission, this accumulates to roughly half a gray, enough to measurably increase cancer risk and cause detectable neurological changes. Over a 20-year crossing to Proxima Centauri at 20% of light speed, the cumulative dose climbs further. Over an 85-year crossing, at 5% of light speed, it becomes severe. Over a multi-century generation ship voyage, it is catastrophic. The biological effects are well documented. High-energy heavy ions, the component of galactic cosmic rays designated as HZE particles, deposit energy along narrow tracks through living tissue. They shatter DNA strands in ways that are qualitatively different from ordinary radiation damage. The breaks are clustered, meaning multiple fractures occur in close proximity along the DNA helix, making repair by the cell's natural machinery far more difficult. Studies using simulated galactic cosmic ray exposures have demonstrated persistent changes in brain structure, including reduced neurogenesis in the hippocampus, the brain region critical for memory and learning. Research published by the National Institutes for Quantum Science and Technology confirms that shielding from galactic cosmic rays remains one of the most significant unresolved safety challenges for any human activity in deep space. No known shielding material fully blocks galactic cosmic rays without adding prohibitive mass to the spacecraft. Hydrogen-rich materials like water or polyethylene can reduce the dose, but they cannot eliminate it. Active magnetic shielding, generating an artificial magnetosphere around the spacecraft, has been proposed but never demonstrated at the required scale. The heavier the shielding, the more fuel is needed to accelerate it, which demands more energy, which adds more mass, which demands more fuel. The problem spirals. Every attempt to protect the crew from radiation makes the spacecraft heavier, which makes the propulsion problem harder, which makes the energy budget larger, which makes the entire mission more impractical. Every propulsion concept that reduces travel time creates new problems that did not exist at lower speeds. Nuclear pulse drives require nuclear weapons in space and produce radioactive contamination. Fusion drives require fuel sources that do not yet exist in accessible quantities. Laser sails require power outputs rivaling national grids and produce uncontrollable, non-decelerating vehicles. Antimatter engines require fuel that takes millions of years to produce and cannot be safely stored. Ramjets create more drag than thrust. Ion drives and nuclear thermal rockets, the technologies closest to current capability, cannot reduce the crossing time below tens of thousands of years. And at any speed high enough to matter, the interstellar medium itself becomes a weapon, eroding surfaces, implanting gas, shattering electronics, and irradiating biological tissue with particles that no practical shielding can fully stop. The instinct is to say that technology will solve these problems. Given enough time and enough funding, humanity will develop shielding materials, miniaturized instruments, radiation-hardened electronics, and energy sources sufficient to push a real spacecraft to a real fraction of light speed. That instinct may be correct, but it ignores a critical asymmetry. The problems created by speed are not engineering challenges that can be overcome with clever design. Some of them are physics. The kinetic energy of a dust grain at 20% of light speed is not a design flaw. It is a consequence of the mass-energy relationship. The radiation dose from galactic cosmic rays is not a funding shortfall. It is a property of the galaxy. The rocket equation is not a bureaucratic obstacle. It is a mathematical law. Solving these problems does not mean outsmarting them. It means finding ways to survive within the constraints they impose. And those constraints are severe enough that no one has yet proposed a credible, fully engineered design for a crewed interstellar spacecraft capable of reaching Proxima Centauri within a human lifetime. So the question shifts. If speed is lethal, what about patience? What if, instead of trying to cross the distance quickly, you accept the crossing will take a very long time? What if you build a ship designed not for speed but for endurance? A ship that can sustain human life for centuries or millennia, crawling across the void at a modest velocity, waiting out the distance rather than trying to outrun it. This is the generation ship concept, and it sounds at first like the most reasonable approach. Avoid the hazards of speed, travel slowly, protect the crew, arrive eventually. But time is not a passive force. Time is an attacker. It corrodes metal. It degrades electronics. It mutates genomes. It fractures societies. And on a journey measured in centuries, time has more than enough opportunity to destroy everything aboard the ship long before it reaches the nearest star. If speed kills, then patience should save you. That is the intuition. Slow down. Remove the hazards of relativistic travel. Avoid the dust impacts, the gas erosion, the savage energy requirements. Build a ship that does not need to move fast, a ship that moves slowly, carefully, conservatively, and simply waits out the distance. Let time do the work instead of velocity. This is the generation ship concept, a spacecraft so large and so self-sufficient that it functions as a miniature world, carrying a human population across the interstellar void at a modest fraction of the speed available from advanced propulsion. Not 20% of light speed, not 5%, perhaps 1% or 0.5% or even less. At 1% of the speed of light, Proxima Centauri is roughly 424 years away. At 0.5%, the crossing stretches to about 850 years. At the speeds achievable with plausible near-future nuclear propulsion, the journey could last 1,000 years or more. Generations of human beings would be born, grow old, and die aboard the vessel without ever seeing the destination. Their grandchildren's grandchildren might be the ones who finally arrive. On paper, this sounds like a solution. You trade speed for endurance. You accept a long journey in exchange for a survivable one. The concept has lived in science fiction for over a century, and serious engineering studies have explored it in detail. But every study reaches the same conclusion. A generation ship does not avoid the problems of interstellar travel. It replaces the fast problems with slow ones. And the slow problems may be worse, because they attack from directions that engineering alone cannot defend. The first response most people have when confronted with the generation ship concept is immediate and confident. Why not just freeze the crew? Put them in suspended animation, let them sleep through the crossing. Wake them up when they arrive. The ship still needs to function for centuries, but it can be automated, maintained by robots, monitored by computers that do not age or grow bored. The crew skips the journey entirely and arrives fresh, young, and ready. This solution is a staple of science fiction. It is not a feature of science. No human being has ever been cryogenically frozen and revived. No mammal of any species has ever been successfully frozen at temperatures cold enough to halt biological processes, stored for any significant duration, and reanimated with brain function intact. The fundamental obstacle is ice. When biological tissue freezes, water inside and between cells forms crystals. These crystals are sharp. They puncture cell membranes, shred intracellular structures, and destroy the delicate architecture of neurons, blood vessels, and organs. The damage is pervasive and, with current technology, irreversible. You can freeze a human being. You cannot unfreeze one. Vitrification, the process of cooling tissue so rapidly that water solidifies into a glass-like state rather than forming crystals, has shown promise in preserving small tissue samples and individual organs. But scaling vitrification to an entire human body requires perfusing every cell with cryoprotectant chemicals at concentrations that are themselves toxic. The process must be performed with extraordinary precision and speed, and reversing it requires equally precise warming to prevent crystal formation during thawing. No one has demonstrated this for an organism larger than a few millimeters. Some researchers have explored torpor, a state of reduced metabolic activity similar to hibernation. NASA funded studies in 2018 examining whether therapeutic hypothermia, which is already used in hospitals to protect brain tissue after cardiac arrest, could be extended to reduce metabolic rate during long-duration spaceflight. The results were modest. Cooling the human body by a few degrees reduces metabolic rate by roughly 5 to 10%. That is helpful for saving supplies on a Mars mission lasting months. It is irrelevant for an interstellar crossing lasting centuries. Reducing metabolic rate by 10% does not turn a 500-year journey into a manageable one. It turns it into a 450-year journey where the crew is slightly cold the entire time. And even if suspended animation were perfected tomorrow, the ship itself still needs to function. A vessel carrying frozen crew members for 500 years still requires power generation, radiation shielding, thermal regulation, navigation, and structural integrity for the entire duration. Someone or something must maintain these systems. Automated maintenance robots would need to operate reliably for centuries without human oversight, repairing failures, replacing components, and adapting to unforeseen problems using artificial intelligence sophisticated enough to substitute for the judgment of trained engineers. No such system exists. No robotic platform has ever been demonstrated to operate autonomously for more than a few years without human intervention. A ship full of frozen crew and failing robots is not a sleeper ship. It is a coffin. So the generation ship must carry a living, waking crew. And that crew faces a biological environment that is hostile in ways that go beyond radiation and genetics. Time is not a passive medium that a spacecraft passes through like a boat through calm water. Time is an active force. It corrodes, degrades, mutates, fractures, and erodes. It works on metal, on circuitry, on biological tissue, on social structures, and on human psychology. A generation ship must survive all of these attacks simultaneously, for centuries, without resupply, without external maintenance, and without any possibility of rescue. There is no harbour between the stars. There is no port of call. If anything fails catastrophically at the midpoint of the journey, the ship and everyone aboard are 500 years from the nearest help in either direction. And help is not coming, because no second ship exists to send. Begin with gravity, or rather, the lack of it. In the weightlessness of space, the human body deteriorates rapidly. Astronauts aboard the International Space Station experience bone density loss of approximately 1 to 2% per month. Muscles atrophy. The cardiovascular system deconditions as the heart no longer works against gravity to pump blood upward. Fluid shifts toward the head, increasing intracranial pressure and causing measurable changes in vision, a condition NASA has designated spaceflight-associated neuroocular syndrome. The immune system weakens. Wound healing slows. Over a 6-month mission, these effects are manageable with daily exercise and medical monitoring. Over a lifetime, they are disabling. Over multiple generations born and raised in weightlessness, the cumulative physiological changes could render the human body incapable of functioning in gravity at all, which is precisely the environment the crew must survive when they arrive at a planetary surface. The only proposed solution is artificial gravity generated by rotating the habitat. Spin the ship or a section of it, and centrifugal force pushes the occupants outward against the walls, simulating the sensation of weight. This works physically. The engineering challenges, however, are severe. To produce a comfortable gravitational environment without nauseating Coriolis effects, the rotation rate must be low, which means the radius must be large. Most studies agree that a minimum radius of roughly 200 to 500 meters is required to keep the rotation rate below 2 revolutions per minute, the threshold above which most people experience persistent motion sickness and disorientation. A habitat with a radius of 500 meters is a structure more than a kilometer across. Spinning it continuously for centuries introduces its own set of mechanical stresses. Bearings wear. Structural elements fatigue under the constant centrifugal loading. Gyroscopic effects complicate navigation and course corrections. The rotating section must be perfectly balanced. Any asymmetry, from cargo shifts, structural damage, or uneven mass distribution, produces vibrations that propagate through the entire vessel. A spinning top that must never wobble for 1,000 years. That is the engineering requirement. Now add genetics. A generation ship carries a living population that must remain genetically viable across dozens of generations. This is not a trivial requirement. Small populations suffer from genetic drift, the random loss of genetic diversity over time. In each generation, Some gene variants fail to pass to offspring simply by chance. Over many generations, these losses accumulate. The population becomes increasingly homogeneous. Rare but essential genetic variations disappear. The capacity to adapt to unexpected environmental challenges diminishes. Eventually, accumulated harmful mutations that would normally be diluted by genetic diversity begin to express themselves at higher rates. Inbreeding depression sets in, even if deliberate inbreeding is avoided, because the population is simply too small for statistical diversity to maintain itself. How many people does a generation ship need? The answer depends on whom you ask, and the range of estimates is disturbingly wide. Mid-20th century studies suggested that a population of 200 to 500 individuals might suffice if carefully managed, with strict breeding protocols to minimize inbreeding and maximize genetic diversity. These numbers assumed a level of reproductive control that most societies would find ethically repugnant, essentially dictating who may reproduce with whom for dozens of consecutive generations. More recent work has challenged these optimistic figures. A 2014 analysis by the anthropologist Cameron Smith argued that the minimum viable population for a multi-century interstellar voyage should be between 10,000 and 40,000 individuals. Smith's estimate accounted not only for genetic diversity, but for cultural redundancy, the need for the population to contain enough specialists, teachers, leaders, and innovators to sustain a functional society even after catastrophic losses from disease, accident, or social disruption. A ship carrying 200 people has no margin for error. A plague that kills half the population leaves 100 survivors, a number so small that genetic collapse may follow within a few generations. A ship carrying 20,000 people can absorb a 50% loss and still maintain a viable breeding population, a functional labour force, and a working knowledge base. But 20,000 people is not a crew. It is a small city. The ship must house, feed, educate, govern, and medically sustain a small city for centuries. The infrastructure required for this dwarfs anything humanity has ever built for space. The International Space Station, the largest structure humans have assembled in orbit, supports a crew of 6 to 7 people and requires constant resupply from Earth. A generation ship for 20,000 would need to be larger by orders of magnitude, and it would receive no resupply of any kind for the entire duration of the voyage. Even if the population size problem is solved, radiation remains. Galactic cosmic rays do not stop being dangerous just because the ship is moving slowly. The dose rate is determined by the interstellar radiation environment, not by the ship's velocity. A generation ship crawling at 0.5% of light speed receives the same daily radiation dose as a faster vessel. The difference is duration. A ship traveling for 100 years accumulates 100 years of cosmic ray exposure. A ship traveling for 1,000 years accumulates 10 times more. Without shielding sufficient to reduce the dose below biologically safe levels, the cumulative genetic damage to the population over centuries of exposure would be devastating. Each generation inherits slightly more radiation-induced mutations than the last. Over dozens of generations, the genome deteriorates, cancer rates climb, fertility drops. The population weakens from within, eroded by particles it cannot see or feel. Now consider the ship itself, not the biology, not the radiation, the machine. No machine in human history has operated continuously for 1,000 years. The statement bears repeating because its implications are so profound, they tend to slide past without registering. Humanity has never built anything, not a clock, not a building, not a bridge, not any device of any kind, that has functioned without maintenance for a millennium. The oldest continuously operating mechanical devices are clocks from the 1300s and 1400s, and they survive only because skilled artisans have maintained, repaired, and rebuilt them across dozens of generations. Remove the artisans and the clocks stop within decades. A generation ship contains millions of moving parts and electronic components. Life support systems must circulate air, purify water, regulate temperature, and manage waste without interruption. Structural seals must remain airtight against the vacuum of space. Propulsion systems, even if only used for minor course corrections, must remain functional across centuries. Power generation systems, whether nuclear fission reactors or radioisotope generators, must continue producing energy long after their designed operational lifetimes. Computer systems must process data, monitor ship functions, and maintain navigational awareness without succumbing to the gradual degradation that time inflicts on all electronic hardware. Metal fatigues. This is not a possibility, it is a certainty. Repeated stress cycles, thermal expansion and contraction, vibration from onboard machinery, all of these forces slowly weaken metal structures at the microscopic level. Tiny cracks form, cracks propagate. Over decades, a structural member that was perfectly sound at launch develops fractures that compromise its load-bearing capacity. On Earth, engineers inspect, repair, and replace fatigued components routinely. On a generation ship 1,000 years from the nearest shipyard, there is no replacement. The crew must manufacture spare parts from onboard materials, using onboard tools, guided by knowledge that must be preserved and transmitted flawlessly across dozens of generations. But manufacturing spare parts is not as simple as that sentence implies. On Earth, producing a single replacement component for a critical system can require an industrial supply chain spanning multiple continents. A computer chip requires a fabrication facility costing tens of billions of dollars, operating in cleanroom conditions, using dozens of rare elements sourced from mines scattered across the globe. A replacement bearing for a centrifugal pump requires specific steel alloys, smelted at precise temperatures, forged or cast using specialized equipment, heat-treated to exact specifications, and machined to tolerances measured in thousandths of a millimeter. A new seal for a life support junction requires polymer chemistry, precision molding, and quality testing under conditions that replicate the operational environment. A generation ship must carry aboard it a meaningful fraction of Earth's entire industrial base, compressed into a volume small enough to fit inside a spacecraft and robust enough to operate for centuries. It must carry machine tools capable of working metal, ceramic, polymer, and composite materials. It must carry feedstock for those tools, either as raw materials or as failed components that can be recycled. It must carry the chemical reagents needed for polymer synthesis, the refining equipment needed for metallurgy, and the precision instruments needed for quality control. And it must carry the expertise to operate all of this, not as a manual stored in a database, but as living knowledge held by trained human specialists who pass their skills to the next generation before they die. This is not the same challenge as mechanical fatigue. It is a second-order challenge. A ship whose oxygen pump breaks is in trouble. A ship that has lost the ability to forge a replacement impeller blade is doomed. The first failure is mechanical, the second is civilizational, and the second is far more likely on a millennial timescale, because manufacturing capability depends on a convergence of materials, equipment, and human knowledge that must all be maintained simultaneously. Lose any one leg of that triad and the capacity to repair vanishes. The ship does not stop functioning immediately. It stops being repairable. And a ship that cannot repair itself is a ship on a countdown, burning through its remaining functional components one by one with no way to replace them. Lubricants break down. Microelectronics degrade under cosmic ray bombardment. Every high-energy particle that passes through a computer chip has a chance of flipping a bit, corrupting stored data, or permanently damaging the transistor it strikes. Over centuries of continuous exposure to the unshielded galactic cosmic ray environment, even hardened electronics accumulate damage, chips fail, memory corrupts, processors develop errors, the ship's computational infrastructure, the nervous system that monitors and controls every function aboard, slowly degrades from causes that are invisible to the crew until a critical system fails. A generation ship is, in essence, a cathedral that must repair itself without stonemasons. The original builders are long dead. The knowledge of how they designed and assembled each component must be preserved in documents, databases, and training programs that themselves are subject to degradation and loss. This is where a danger emerges that is distinct from mechanical failure or manufacturing collapse. It is the danger of knowledge loss, not the loss of a component. The loss of the understanding needed to build or fix the component. Knowledge loss is one of the most consistent features of isolated civilizations throughout human history. The Roman Empire perfected a formula for hydraulic concrete that could set underwater, enabling the construction of harbours, aqueducts, and structures that endured for millennia. After the fall of the Western Empire, the formula was lost. European builders did not rediscover comparable concrete technology for over 1,000 years. Medieval masons could admire Roman aqueducts, but could not replicate them. The knowledge simply ceased to exist in any accessible form. The same pattern repeats throughout history. Greek fire, the incendiary weapon of the Byzantine Empire, was lost so completely that modern chemists still debate its composition. Stradivarius violins have never been replicated despite centuries of effort, because whatever Antonio Stradivari knew about wood treatment, varnish, and construction died with him and his sons. Damascus steel, prized for its strength and flexibility, vanished as a manufacturing technique in the 1800s, when the specific ore sources were exhausted and the smelting methods were never recorded with sufficient precision. On Earth, knowledge survives because it is distributed. It exists in millions of libraries, billions of documents, and a global network of universities, laboratories, and professional communities. When one institution loses knowledge, another preserves it. When one expert dies, others continue the tradition. The redundancy is planetary in scale. A generation ship has none of this. It is a library with no librarian and shelves that slowly dissolve. All technical knowledge aboard the ship exists in a finite number of copies, stored on media subject to degradation, taught by instructors who are mortal and learned by students who must prioritize what to study based on the immediate needs of a society under constant pressure. If Generation 15 fails to train enough metallurgists because the educational curriculum was revised by Generation 12 to prioritize agriculture after a food crisis, the ability to repair structural steel is not broken. It is gone. The knowledge ceases to exist aboard the ship. On Earth, you could consult a textbook, travel to a university, or hire a specialist from another country. On a generation ship, there is no other country. There is no specialist to import. The expertise is aboard or it is nowhere. Every critical skill aboard the ship follows this pattern. Reactor physics, semiconductor fabrication, agricultural genetics, water chemistry, orbital mechanics, structural engineering, medical surgery. Each discipline requires years of training to master and must be transmitted intact from one generation to the next without interruption. A single generation that fails to produce a qualified nuclear engineer leaves the ship without anyone who understands the power source. A single generation that fails to produce a qualified ecologist leaves the ship without anyone who can diagnose why the oxygen levels are dropping. The cascade from knowledge loss to system failure to civilizational decline can begin with something as mundane as an unpopular course that not enough students choose to study. Now consider the ecology. A generation ship must sustain a closed-loop biosphere, a self-contained system that recycles all air, water, food, and waste without any external input. Earth does this effortlessly, using an entire planet's worth of ocean, atmosphere, soil, and biodiversity to maintain chemical equilibrium. A generation ship must replicate this balance inside a sealed metal hull, using a tiny fraction of Earth's biological complexity for centuries without interruption. The most ambitious closed ecology experiment ever attempted was Biosphere 2, a 3-acre enclosed facility in Arizona that operated between 1991 and 1993. The facility was designed to be a completely sealed, self-sustaining ecosystem supporting 8 human inhabitants. It contained a rainforest, a desert, a coral reef, agricultural areas, and a small ocean. The project cost over $200 million and was built with the full resources of Earth-based engineering and biology. It failed. Oxygen levels dropped from 21% to 14%, equivalent to conditions at an altitude of roughly 13,000 feet above sea level. Carbon dioxide levels fluctuated wildly. Crop yields fell short of requirements. Insect pollinators died. Pest species thrived. The concrete structure of the facility itself absorbed oxygen through a chemical reaction that no one had anticipated, silently draining the atmosphere of the gas the crew needed to breathe. The 8 inhabitants suffered from chronic hunger and low oxygen for months before the experiment was ended. Biosphere 2 lasted 2 years. A generation ship must sustain its ecology for 500. Every ecology on Earth is stabilized by its connection to the planetary system. A generation ship has none of these buffers. Its ecology is a candle flame on a raft crossing the Pacific. Any gust, any leak, any unforeseen chemical interaction, and the flame goes out. Relighting it may not be possible. And then there is the challenge that no engineering diagram can address: the human mind. A generation ship is not merely a vehicle, it is a society. A complete, enclosed, isolated human civilization that must maintain its coherence, its purpose, and its functional capacity across more generations than most civilizations on Earth have ever survived. Consider what has happened to human societies over spans of 500 or 1,000 years. Languages evolve beyond mutual intelligibility. Religions transform, split, and vanish. Political systems rise, collapse, and are replaced by structures their founders would not recognize. A generation ship launches with a mission: reach Proxima Centauri. The first generation understands this mission because they chose it. They left Earth voluntarily. They knew what they were signing up for. Their children inherit some of this motivation. Their grandchildren inherit less. By the 5th generation, Earth is not a memory. It is a story. By the 10th, it is a myth. By the 20th, the mission itself may feel less like a sacred purpose and more like an inherited obligation imposed by ancestors who are centuries dead. This is where the ethics of the generation ship become impossible to ignore. The first generation chooses the mission. Every generation after the first does not. They are born into a metal enclosure they cannot leave, committed to a journey they never agreed to, living and dying inside a vessel whose destination they will never see. They are, by any meaningful definition, conscripts. Their lives are defined not by their own choices but by a decision made by ancestors they never met. People who weighed the potential of reaching another star against the certainty of confining their descendants to a sealed tube for centuries. The ancestors chose exploration. The descendants inherit imprisonment. This is not a philosophical edge case. It is the central moral reality of every generation ship. Every person born aboard after the first crew is a person whose entire existence was determined by someone else's ambition. They cannot leave. They cannot opt out. They cannot turn the ship around and go home, because home is centuries behind them and the fuel for a return journey does not exist. Their only option is to continue, to live their lives inside the hull, to raise children who will also live their lives inside the hull, and to die knowing that their contribution to the mission was merely surviving long enough to produce the next generation of conscripts. Serious generation ship studies acknowledge this problem explicitly. The 2025 Project Hyperion Chrysalis design study, one of the most detailed recent generation ship architectures, proposed that prospective crew members live for multiple generations in Antarctic isolation before launch, to test their suitability for enclosed long-duration life. The proposal implicitly acknowledges that not all humans can thrive under these conditions, and that selecting for psychological resilience is as important as selecting for physical health. But no amount of pre-selection can address the fundamental problem. The crew's children did not undergo selection. They were born, and they were born into a world they cannot escape. Mission drift compounds the ethical crisis. History is littered with evidence that long-duration human institutions change beyond recognition over centuries. A generation ship's mission must survive this process intact, because if the crew of Generation 30 decides that the mission no longer matters, the journey fails, not through mechanical breakdown, through human choice. Social collapse poses an even starker threat. The Mars 500 experiment, which confined 6 volunteers in a simulated spacecraft for 520 days, documented significant psychological stress, sleep disruption, and interpersonal conflict even in a group that knew the simulation would end. A generation ship offers no such assurance. Mutiny, schism, and factional violence are not edge cases on a millennial timescale. They are near certainties. And beneath the social dynamics, beneath the ethical dilemmas, there is a threat even more fundamental. The human brain evolved on Earth. It evolved in an environment of constant sensory variation. Seasons change. Weather shifts. Light varies from dawn to dusk and from summer to winter. Landscapes differ from place to place. Sounds, smells, temperatures, and textures fluctuate in ways the brain has evolved over millions of years to expect, process, and need. Remove that variation and the brain begins to suffer in measurable ways. Studies on sensory deprivation demonstrate cognitive decline, perceptual distortion, hallucinations, and emotional flattening within days of reduced environmental stimulation. Submarine crews, Antarctic winter-over personnel, and long-duration space station inhabitants all report a phenomenon sometimes described as the third quarter effect, a period of pronounced psychological deterioration roughly 3/4 of the way through a confined mission, when the monotony becomes unbearable and the end is not yet close enough to provide motivational relief. Performance drops, conflicts spike, depression deepens, creativity dries up. The brain, starved of input, turns inward and begins to malfunction. A generation ship imposes the most extreme version of this monotony that any human being would ever experience. The corridors never change, the lighting is artificial and constant, the recycled air carries the same faint chemical signature every day. There are no new faces after launch, no new landscapes, no horizon that is not a wall, no wind, no rain, no seasons, no variation of any kind beyond what the crew can manufacture through deliberate effort. And this monotony does not last for months. It does not last for years. It lasts for lifetimes. Entire generations would be born, grow up, grow old, and die, having never experienced a single moment of environmental novelty that was not artificially created by someone who was also suffering from the same deprivation. The neurological consequences of this are unstudied at the required timescale, because no experiment has ever lasted long enough to measure them. But the direction of the effect is consistent across every shorter duration study that exists. Monotony degrades cognition. It erodes motivation. It flattens emotional range. It reduces the brain's ability to solve novel problems, which is precisely the ability the crew needs most when a system fails unexpectedly. Scaling that degradation to a lifetime, and then to dozens of consecutive lifetimes, suggests a population that is not merely unhappy, but neurologically diminished. A crew whose capacity to think clearly, to respond creatively to emergencies, and to maintain the motivation required for a multi-century mission erodes with each generation, not because of radiation or genetic drift, but because their brains never receive the stimulation they evolved to require. The ship becomes quieter, not in volume, in thought. Through all of this, the crew is alone, truly, physically, irreversibly alone, in a way that no human community in history has ever experienced. The communication delay to Earth is not a minor inconvenience. At the midpoint of the journey, a radio signal takes over 2 light years to reach Earth. A round-trip exchange takes over 4 years. There is no rescue ship. There is no supply convoy. There is no cavalry. If the life support system fails at the 600-year mark, no force in the universe can help the crew faster than the speed of light allows, and the speed of light is far too slow. This isolation is not merely physical, it is psychological. Every person aboard the ship lives with the knowledge that they are the most remote human beings who have ever existed. The nearest other humans are years away at the speed of light. The nearest breathable atmosphere is behind them, receding at whatever velocity the ship maintains. Studies of Antarctic research stations, submarines, and long-duration space missions consistently document elevated rates of depression, anxiety, interpersonal conflict, and cognitive decline in isolated populations. These studies involve missions lasting months or years, with the certain knowledge that the isolation will end. A generation ship offers no such certainty. The isolation is the mission. It does not end until arrival, and arrival is centuries away. The generation ship concept asks humanity to do something it has never done: sustain a sealed ecology for centuries without failure, maintain a complex machine for millennia without irreplaceable parts, preserve a global industrial base inside a single hull, prevent the loss of critical knowledge across dozens of generations with no external backup, preserve a stable society without external contact, protect a living population from cumulative radiation damage without perfect shielding, provide artificial gravity without mechanical failure, freeze no one because the technology does not exist, shield the crew's minds from a monotony so total it degrades the brain itself, and commit generation after generation of human beings to a life they did not choose, in a vessel they cannot leave, pursuing a mission that was defined before they were born. Each of these challenges, taken individually, pushes against the limits of human capability. Taken together, they form a wall so high that no proposed generation ship design has ever credibly demonstrated the ability to clear it. And yet, suppose it works. Suppose the ecology holds. Suppose the machines are maintained. Suppose the knowledge survives. Suppose the society remains coherent. Suppose the population stays healthy and alert. The destination star appears in the forward viewports, growing brighter with each passing year. That should be the moment of triumph. 1,000 years of endurance rewarded. 100 generations of sacrifice vindicated. The nearest star reached at last. But reaching a star and surviving its arrival are not the same thing. The ship must still slow down. It must still navigate the Proxima Centauri system. It must still function in an environment that, as it turns out, is actively hostile. Arrival is not the end of the crisis. Arrival is a new crisis, and the ship, after centuries of slow degradation, may not be equipped to survive it. Imagine you have crossed an ocean, not in days or weeks, but across generations. Your great-great-grandparents built the vessel. Your great-grandparents launched it. Your grandparents maintained it through its worst mechanical crises. Your parents were born in the deep middle of the crossing, knowing nothing but the interior of the ship and the black void outside. You have spent your entire life watching a single dim red point of light grow slowly brighter in the forward viewport. That light is Proxima Centauri, the destination, the reason the ship exists, the reason you exist. And now, after centuries of endurance, the star is close enough to resolve as a disk, close enough to detect its planets, close enough that the journey, at last, appears to be ending. This should be triumph. It is not, because the ship is still moving, and unless it can stop, everything your ancestors sacrificed, every generation that lived and died inside the hull, every system that was painstakingly maintained across centuries of flight, all of it amounts to nothing. The ship will pass through the Proxima Centauri system at whatever velocity it has been carrying since the acceleration phase ended. If that velocity is 1% of the speed of light, the ship crosses the entire Proxima Centauri system in under 2 hours. The planet itself is within useful observation range for only minutes. Minutes. Centuries of travel reduced to a momentary blur. The crew catches a fleeting glimpse and then watches the world shrink into the blackness behind them. The crossing continues. There is no destination. There is only a flyby so brief it barely qualifies as an observation. This is the braking problem, and it is among the most severe, least discussed, and most demoralizing challenges in all of interstellar mission design. Deceleration requires energy. In most practical terms, it requires approximately the same amount of energy as acceleration. A ship that spent years or decades accelerating to its cruising velocity must spend a comparable effort slowing down. For a conventional rocket, this means carrying enough fuel not only to reach interstellar speed, but to shed that speed upon arrival. The rocket equation, already punishing during acceleration, doubles its cruelty. The fuel required to decelerate must itself be accelerated during the first phase of the journey, which means carrying fuel to accelerate the deceleration fuel, which means more fuel still. The mass ratios become absurd. For a ship that must both accelerate to and decelerate from 5% of light speed, the fuel-to-payload ratio climbs into the thousands. The ship at launch is almost entirely fuel. The payload, the habitat, the crew, the life support systems, all of it becomes a vanishingly small fraction of the total mass. Some designs avoid this problem by simply not decelerating. Breakthrough Starshot, for example, was designed explicitly as a flyby mission. Its gram-scale probes would blast through the Alpha Centauri system at 20% of the speed of light, spending only hours within range of any planet. No braking, no orbit, no lingering. For an uncrewed probe weighing 1 gram, this is an acceptable compromise. For a crewed generation ship carrying 20,000 people, it is meaningless. You do not spend 1,000 years crossing interstellar space to spend a few minutes at the destination. The interstellar medium itself offers no help. In atmospheric flight, a vehicle can use air resistance to decelerate. Between the stars, there is no atmosphere. The interstellar medium is so thin, roughly 1 atom per cubic centimetre, that it provides no measurable drag at any velocity. A ship cannot aerobrake in interstellar space. The void is too empty to slow anything down. Magnetic sails have been proposed as an alternative. A magnetic sail generates a large magnetic field around the spacecraft, which interacts with the charged particles of the interstellar medium to produce drag. In theory, this drag accumulates over time and gradually decelerates the ship. In practice, the interstellar medium is so sparse that the deceleration rate is extremely low. For a ship traveling at several percent of light speed, the magnetic sail provides insufficient braking force to achieve orbital insertion at the destination. It might reduce the flyby velocity enough to extend the observation window from seconds to hours, but it cannot stop the ship. The most creative proposed solution came from the physicists René Heller and Michael Hipke, who published their concept in 2017. They proposed using the radiation pressure and gravity of the destination stars themselves to decelerate an incoming light sail. The idea exploits the fact that Alpha Centauri is a triple star system. A sail-equipped probe approaching the system could deploy its sail to catch photon pressure from Alpha Centauri A, the brightest star in the system. The radiation pressure would push against the sail, decelerating the probe. Simultaneously, the probe would use a carefully calculated gravitational slingshot around Alpha Centauri A to redirect its trajectory toward Alpha Centauri B. There, another radiation braking maneuver would further reduce velocity. Finally, the probe would be redirected toward Proxima Centauri, arriving at the dim red dwarf after an additional 46 years of travel. The total mission duration from Earth to Proxima Centauri, using this photogravitational assist technique, would be approximately 140 years. The concept works mathematically, but it applies only to ultralight sail probes. Heller and Hipke's calculations assumed a total spacecraft mass of less than 100 grams, mounted on a sail with a surface area of 100,000 square meters. That is a sail roughly 316 meters on a side, larger than 3 football fields, carrying a payload lighter than a bar of soap. For a crewed vessel massing thousands or millions of tons, photon pressure from even a bright star provides negligible deceleration force. The physics does not scale. Robert Forward, one of the pioneers of interstellar sail theory, proposed a different approach in his 1984 paper on round-trip interstellar travel using laser-pushed light sails. Forward envisioned a stage sail system where the sail separates into an outer ring and an inner disk upon approaching the destination. The Earth-based laser illuminates the outer ring, which reflects the beam back onto the inner disk, decelerating it. The concept is ingenious but demands a laser powerful enough to maintain a focused beam across 4.24 light-years. Forward proposed a massive Fresnel lens, hundreds of kilometers in diameter, positioned between the solar system and the destination to refocus the beam. Building a lens hundreds of kilometers across in deep space is not a proposal. It is a prayer. For a crewed interstellar mission, no credible, fully engineered braking solution currently exists. Every proposed method either works only for ultralight probes, requires infrastructure that does not exist and cannot currently be built, or demands fuel masses that make the mission impractical. The braking problem is not a detail to be worked out later. It is a fundamental barrier. A ship that cannot stop is not a vehicle, it is a projectile, and a projectile does not explore, it passes through. Suppose, despite everything, the ship stops. Suppose a braking technology is developed that allows a crewed vessel to decelerate from interstellar cruising speed into a bound orbit around Proxima Centauri. The crew has arrived, the journey is over. What do they find? They may not even know what to expect. This is one of the least discussed aspects of interstellar travel, and it is among the most disorienting. By the time a generation ship arrives at Proxima Centauri, the observations that define the mission will be centuries old. The discovery of Proxima B was announced in 2016. A ship launched a century from now, using the best available data at that time, would arrive centuries after that. During the crossing, telescopes on Earth and in the solar system will have continued observing the Proxima Centauri system. They may have detected an atmosphere on Proxima B or confirmed its absence. They may have discovered additional planets. They may have revised orbital parameters, updated mass estimates, or reclassified the system entirely based on data collected with instruments that did not exist when the ship launched. But the crew only receives this updated information at the speed of light, and only if Earth continues transmitting it. If communication degrades during the voyage, if transmitter arrays on Earth are decommissioned or repurposed, if the civilization that launched the ship transforms to the point where maintaining contact with a centuries-old mission is no longer a priority, the crew arrives with a target description that is hundreds of years out of date. They are navigating by a map drawn by a civilization that may no longer exist in recognizable form. The Proxima Centauri system they encounter may look nothing like the system described in their mission files. Planets may have been rediscovered, reclassified, or found to be artifacts of measurement error. The crew steps into the unknown armed with ancient data, and there is no one to ask for corrections. What they find, based on what we currently know, is a star that is trying to kill them. Proxima Centauri is a flare star. This designation is not metaphorical. It means the star produces sudden, violent outbursts of electromagnetic radiation and charged particles at irregular intervals. These flares are not gentle fluctuations. They are explosions. In April 2021, astronomers observed a flare from Proxima Centauri that released energy 100 times greater than any solar flare ever recorded from our Sun. The eruption spanned the electromagnetic spectrum, from radio waves through visible light to X-rays and ultraviolet radiation. For any planet orbiting close to the star, such an event represents a bombardment of sterilizing intensity. Proxima b orbits very close to its star. Its orbital distance is approximately 0.048 astronomical units, roughly 20 times closer to Proxima Centauri than Earth is to the Sun. At this distance, the planet sits within the habitable zone, the region where surface temperatures could theoretically allow liquid water. But the habitable zone of a red dwarf is a narrow band perilously close to a violent star. Proximity to the habitable zone means proximity to the flares. Research led by Ignacy Ribas and colleagues estimated that Proxima b currently receives approximately 30 times Earth's extreme ultraviolet flux and roughly 250 times Earth's X-ray flux. These are not conditions that favor the retention of an atmosphere. NASA modeling, based on observations from the Chandra X-ray Observatory, demonstrated that Proxima Centauri's radiation environment could strip an Earth-like atmosphere up to 10,000 times faster than atmospheric loss occurs on Earth. The planet may have lost any substantial atmosphere billions of years ago. A 2025 study using the ALMA radio telescope array placed the first constraints on Proxima Centauri's millimeter wavelength flare rates, reinforcing the emerging consensus that Proxima Centauri's stellar environment is deeply hostile to atmospheric retention and surface habitability. This does not definitively prove that Proxima b is airless. A planet with a strong magnetic field and a thick initial atmosphere might retain enough gas to remain habitable, but the balance of evidence, as of current observations, leans toward pessimism, and Proxima b is the best option in the system. The other known planets offer nothing better. Proxima d, confirmed in 2025, orbits so close to the star that its surface temperature reaches approximately 360 Kelvin, roughly 87 degrees Celsius. That is close to the boiling point of water, a world bathed in heat, tidally locked, so that one face permanently stares into the red dwarf's radiation while the other faces the void. It is not a destination. It is an oven. Proxima c, if it exists, orbits much farther out, at roughly 1.5 astronomical units from the star. At that distance, it sits well outside the habitable zone of a dim red dwarf. Surface temperatures would be far below freezing. Its estimated mass, if the detection holds, suggests a super-Earth or mini-Neptune, a world with no solid surface to land on, or with a surface buried beneath a crushing atmosphere of hydrogen and helium. Proxima c is not an alternative to Proxima b. It is a frozen giant orbiting in permanent darkness, irrelevant to any crew hoping to find a habitable world. The system may contain no viable target at all. 3 known planets, and not one of them is clearly capable of supporting human life. The crew has arrived at the nearest star system after centuries of travel and found a flare-blasted rock, a tidally locked furnace, and a frozen gas world. This is not a catastrophic surprise. It is the predictable outcome of sending humans to a star whose planetary system was never confirmed to be habitable, only suspected to be potentially interesting. The word habitable zone does not mean habitable. It means the right temperature for liquid water on a planet that has an atmosphere, and Proxima b may not have an atmosphere. The crew of the arriving generation ship would face this reality with no backup plan. They have travelled for centuries to reach a system whose most promising planet may have no breathable atmosphere, no liquid water on its surface, and no protection from stellar flares that occur without warning. The ship, after centuries of mechanical degradation, may not be equipped for an extended stay in orbit. Its systems were designed to reach the destination, not to sustain operations indefinitely after arrival. Fuel reserves, if any remain, are depleted. Spare parts have been consumed over generations of in-flight maintenance. The closed-loop ecology, stressed by centuries of operation, may be approaching the limits of its capacity. So what does the crew do? They cannot go home. A return journey to Earth would require fuel the ship does not carry, for a crossing as long as the one they just completed, to a planet that has changed beyond recognition in the intervening centuries. The Earth they left no longer exists. Not physically, the planet is still there, but culturally, politically, and perhaps even linguistically. A civilization that departed Earth 1,000 years ago would return to find a world as alien to them as any exoplanet. The languages have changed. The governments have changed. The technology has changed. The crew's descendants would arrive as strangers, refugees from a forgotten era, carrying outdated knowledge and obsolete skills, assuming anyone on Earth remembered they were coming at all. They cannot land, because there may be nowhere to land. Even if Proxima b has a surface, it may be irradiated, airless, and geologically dead. Establishing a colony on such a world would require constructing sealed habitats from scratch, using materials mined from the planet or from asteroids in the system, with equipment designed for the solar system's composition, not Proxima Centauri's. The mineral and chemical makeup of the Proxima system is unknown. Ore deposits, atmospheric chemistry, regolith composition, none of these have been characterized. The crew would be mining a world they do not understand, with tools that may not be appropriate to build shelters against conditions they have never experienced. They could remain in orbit. But an orbital existence is simply a continuation of the generation ship, minus the destination. The ship becomes a space station orbiting a hostile star, sustained by a degraded ecology and aging systems, with no prospect of improvement and no external supply chain. The crew lives and dies in orbit around a world they can see but cannot use. They are a swimmer who has crossed an ocean only to find the shore on fire. And the crew cannot ask for help. A radio message to Earth travels at the speed of light. It arrives 4.24 years after transmission. Any reply takes another 4.24 years to return. The round-trip communication time is approximately 8.5 years. The exchange is not a conversation. It is a letter that arrives years after the sender and recipient have both moved on from the moment that prompted it. The communication delay does more than prevent real-time assistance. It severs the psychological connection between the crew and the rest of humanity. The crew must make survival decisions in real time. They must assess the Proxima Centauri system, evaluate the habitability of its planets, determine whether orbital resources can sustain them, and plan their next steps, all without input from Earth. They are the most isolated human beings who have ever existed, and the decisions they make in the first days and weeks after arrival will determine whether the mission produces a surviving colony, a temporary outpost, or a tomb. Consider the emotional weight that falls on these people. They did not choose this mission. Their ancestors chose it. They were born into a metal shell, raised on recycled air and artificial light, educated in the history and purpose of a voyage that began before their grandparents were born. They have never felt rain. They have never seen an open horizon. They have never breathed air that was not mechanically processed. Their entire lives have been defined by the promise that the destination would make the sacrifice worthwhile. And now they have arrived, and the destination may be a barren rock orbiting a star that intermittently tries to sterilize everything within reach. This is the moment when the word nearby completes its collapse. Proxima Centauri is 4.24 light-years from our Sun. In galactic terms, this is nothing. The Milky Way spans 100,000 light-years. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The observable universe stretches 93 billion light-years from edge to edge. Against this backdrop, 4.24 light-years is so small it barely registers. Astronomers are correct when they say that Proxima Centauri is close. On the scale of the galaxy, it is. But human beings do not live on the scale of the galaxy. Human beings live on the scale of human bodies, human lifetimes, human engineering, and human societies. On that scale, 4.24 light-years is not close. It is a barrier so vast and so hostile that crossing it requires solving every problem simultaneously. Propulsion, shielding, energy, ecology, medicine, genetics, sociology, psychology, communication, braking, and survival at the destination. Failure in any single domain ends the mission. And success in every domain has never been achieved even for missions lasting a few years, let alone centuries or millennia. The distance to Proxima Centauri is approximately 25 trillion miles. That number is not simply large. It is large in a way that breaks the relationship between distance and reachability that has governed all of human exploration. Every frontier humanity has ever crossed, from one continent to the next, from the surface to the sky, from the Earth to the moon, was a frontier where the gap could be bridged by extending existing capability. Ships became faster, airplanes flew higher, rockets burned harder. Each step stretched the same underlying technology further. Interstellar space does not work this way. The gap between the solar system and Proxima Centauri is not an extension of the gap between Earth and Mars. It is a categorically different kind of distance. It requires not incremental improvement but transformation, a wholesale reinvention of what spacecraft are, how long they last, how many people they carry, and what it means to sustain human life in absolute isolation for timescales that exceed the lifespan of civilizations. This is not a pessimistic conclusion. It is a factual one. No current or near-future technology can send human beings to Proxima Centauri and bring them back alive. No proposed generation ship design has demonstrated the ability to sustain a closed ecology for centuries. No propulsion system has been tested at even a fraction of the velocity required for interstellar transit. No shielding system can fully protect a crew from galactic cosmic rays over multi-decade exposures. No braking technology can stop a crewed vessel at the destination. And the destination itself, the nearest potentially habitable planet in the universe, orbits a star whose radiation environment may have rendered it permanently uninhabitable. The rest of the system offers no better alternative. Every path to Proxima Centauri is a path through crisis. Go fast and the interstellar medium tears the ship apart. Go slow and time tears the crew apart. Sleep through it and the technology does not exist to wake you. Spin the habitat for gravity and the bearings must last a millennium. Arrive without braking and the destination vanishes in seconds. Arrive with braking and the star may have already destroyed the only planet worth visiting. Land and the surface may be hostile. Orbit and the ship becomes a permanent prison. Go home and home no longer knows you. Communicate with Earth and the delay renders every exchange a monologue delivered to an empty room. Arrive with ancient data and the destination you planned for may not match the destination you find. The mission is not merely difficult, it is difficult in every dimension simultaneously, and the dimensions are coupled so that solving one problem often worsens another. Humanity may one day develop the technology to reach Proxima Centauri. That possibility cannot be dismissed. The history of technology is a history of solving problems that appeared insoluble. Powered flight was impossible until it was not. Reaching the moon was fantasy until it was engineering. But interstellar travel is not one problem. It is dozens of problems stacked on top of each other, each one requiring a breakthrough, and all of them requiring solutions that work together across timescales that no human enterprise has ever sustained. The horrifying truth about Proxima Centauri is not that it is far away. Every star is far away. The horrifying truth is that it is the closest star, the absolute best case, the shortest possible interstellar journey, and it is still separated from us by a barrier that exceeds the natural scale of human engineering, human biology, and human civilization. If the nearest star is this hard to reach, then no star is easy. The galaxy that contains 400 billion suns is, for all practical purposes, a collection of islands separated by uncrossable oceans. Each star system is its own world, isolated from its neighbours by distances that light itself needs years to traverse, and that spacecraft would need centuries or millennia to cross. The Sun is our star. The solar system is our home, and beyond it, the nearest door opens into a hallway so long and so dark and so filled with invisible hazards that the act of walking through it would require humanity to become something it has never been. A species that can sustain itself in absolute isolation for centuries. A species that can build machines that function for millennia. A species that can maintain a stable society without external contact, without rescue, without the psychological anchor of knowing that home is reachable. We are not that species, not yet, and the distance to becoming that species may be measured not in light years but in centuries of technological and social evolution that we cannot shortcut or skip. Proxima Centauri is our nearest neighbour. That sentence should bring comfort. Instead, it delivers the most unsettling revelation in all of astronomy. If this is what nearby looks like, then the universe is not a place built for travellers. It is a place built for prisoners. Each star system is a cell. The walls are made of distance, radiation, time, and the absolute indifference of physics to human ambition. We can see the other cells. We can study them. We can catalogue the prisoners in them, if any exist. But the hallway between cells is so long that the act of crossing it may be permanently beyond what a biological species, living on biological timescales, with biological needs and biological fragility, can endure. The word nearby is the cruelest word in astronomy. It implies that reaching Proxima Centauri is a matter of degree, a harder version of reaching Mars, a longer version of reaching Pluto. It is not. It is a matter of kind. The interstellar crossing is not a longer trip. It is a different category of existence. And until humanity develops the capacity to survive that category, the nearest star will remain what it has always been: visible, studied, measured, named, and utterly, completely, terrifyingly beyond reach.